Good morning. Today we will study lattice, sublattice and modular lattice. In previous lecture we had defined lattice. Lattice is a partially ordered set in which every pair of elements contains least upper bound and greatest lower bound. Now we will study some examples related to lattice. Means we will show that the given poset is a lattice or not. Suppose we have this poset whose Hasse diagram is given. It means this is the element A, this is the element B, and this is the element C, and this is the element D. We have to show that this is a lattice or no, not. So first of all, we will make closure table for this uh, and we will see that every pair of elements contains least upper bound and greatest lower bound or not. We write all the elements ABC this side and all the elements ABC this side. We know that least upper bound is denoted by uh, join. It means A join BA is equal to A. Means least upper bound of A and A is A. Least upper bound of A and B is B. Least upper bound of A and C is C. Least upper bound of A and D is D in this diagram. Now this B and A. Least upper bound of B and A is B. Least upper bound of B and B is B. Least upper bound of B and C is C. Least upper bound of B and D is D. So this is D, this is C. Now C with A, B, C, D. Least upper bound of C and A is C. Least upper bound of C and B is C. Least upper bound of C and D is D. So this is the least upper bound of C and A, C, C and B, C, C and C, C, C and D, D. Now with D, D and A, D and B, D and C and D and D. So least upper bound of D and A is D. D and B is D. C and D is D. And D and D is D. So from this table we see that every pair of elements contains least upper bound. Now we will find greatest lower bound and we denote it by meet. For greatest lower bound of A and A is A. A and B, for A and B, greatest lower bound is A. For A and C, greatest lower bound is A. For A and D, greatest lower bound is A. So this is A. Greatest lower bound means greatest among the lower bounds. Least upper bound means least among the upper bounds. Now B and A. Greatest lower bound of B and A is A. Greatest lower bound of B and B is B. Greatest lower bound B and C is B. Greatest lower bound of B and D is B. So this is B and this is A. Now C with A. Greatest lower bound of C and A is A. Greatest lower bound of C and B is B. Greatest lower bound of C and C is C. Greatest lower bound of C and D is C. So this is A, B, C, C. Now D with A, D with B, D with C, D with D. Greatest lower bound of D and A is A. Greatest lower bound of D and B is B. Greatest lower bound of D and C is C. Greatest lower bound of D with D is D. So every pair of elements contains a greatest lower bound because these elements belong to the set containing A, B, C, D. It means this is a lattice. Now one more example. Suppose this is the Hasse diagram of some another lattice which consists of elements A, B, C and D. And from this diagram we will calculate least upper bound and greatest lower bound for every pair of elements, and we will see that it is a lattice or not. So from this diagram, this is the join means least upper bound, and this is meet means greatest lower bound. So from this figure, great least upper bound of A and A is A. Least upper bound of A and B is B. Least upper bound of A and D is, first A and C is C. Least upper bound of A and D is D. Now with B. Least upper bound of B and A is B. Least upper bound of B and B is B. Least upper bound of B and C is C. Least upper bound of B and D is C. See, least upper bound of B and D is C. Now with C, least upper bound of C and A is C. Least upper bound of C and B is C. Least upper bound of C and D is C. Least upper bound of C and C is C. So we have all C's here. Now with D, least upper bound of D and A is D. Least upper bound of D and B is C. Least upper bound of D and C is C. Least upper bound of D with D is D. So D, C, C and D. Now greatest lower bound. Greatest lower bound of A and A is A. Greatest lower bound of A and B is A, because this is the least element, A. Greatest lower bound of A and C is A. Greatest lower bound of A and D is A. So these are all A's. Now with B, greatest lower bound of B and A is A. Greatest lower bound of B and B is B. Greatest lower bound of B and C is B. Greatest lower bound of B and D is A. Here this is B, this is D, and greatest lower bound is this element, A. Now with C, greatest lower bound of C and A is A. Greatest lower bound of C and B is B. Greatest lower bound of C with C is C. Greatest lower bound of C and D is D. So this is A, D, D. So every pair of elements contains greatest lower bound. So this is a lattice. One more example. Suppose this is the given POSIT. Now we will verify that it is a lattice or not. It will be a lattice if every pair of elements contains greatest lower bound as well as least upper bound. Otherwise, it will not be a lattice. It will only be a partially ordered set or POSIT. So in this diagram, least upper bound of A and A is A. Least upper bound of A and B is A. Least upper bound of A and C is A. Least upper bound of A and D is D. Least upper bound of A and E is E. Least upper bound of A and F is F. Least upper bound of A and G is G. So A, B, C, D, E, F, G. Now least upper bound of B and A is B. Least upper bound of B with B is B. Least upper bound of B and D is D. Least upper bound of B and E is E. Least upper bound of B and F is F. Least upper bound of B and G is G. Now with C, least upper bound of C and A is C. C with B is D. C and D is D. C and E is E. C and F is F. C and G is G. So it is clear from this figure. Now similarly with D, least upper bound of D and A is D. D and B is D. D and C is D. D and E is E. D and F is F. D and G is G. Now with E. Least upper bound of E and A is E. Least upper bound of E and B is E. Least upper bound of E and C is E. Least upper bound of E and D is E. Least upper bound of E and F is F. Least upper bound of E and G is G. Now with F. Least upper bound of F and A is F. Least upper bound of F and B is F. F and C is F. F and D is F. F and E is F. F and F is F. And F and G is, there is no least upper bound for F and G. So, least upper bound of F and G does not exist. Now with G, least upper bound of G and A is G. G and B is G. G and C is G. G and D is G. G and E is G. G and F is, least upper bound of G and F does not exist. And least upper bound of G and G is G. So least upper bound of F with G does not exist. Least upper bound of G and F does not exist. It is clear from the figure F and G does not have least upper bound. Now similarly we can find greatest lower bound. Greatest lower bound of A and A is A. Greatest lower bound of A and B is A. Greatest lower bound of C and A is A. Greatest lower bound of C and D and A is A. Greatest lower bound of E and A is A. Greatest lower bound of F and A is A. Greatest lower bound of G and A is A. Similarly, we can calculate greatest lower bound for all the pair of elements. So, this poset is not a lattice because every pair of element does not contain the least upper bound. However, every pair of element contains greatest lower bound. This can be seen from this closure table. Now suppose this is the given poset. In this case, one may verify that least upper bound of A with A is A. Least upper bound of A and B is B. Least upper bound of A and C is C. Least upper bound of A with E is E. Least upper bound of A with F is F. Least upper bound of A with G, this is G here, is G. So similarly we can calculate least upper bound with B, least upper bound with D, C, E, F and G. Here it is G. Now the greatest lower bound. Greatest lower bound of A and A is A. Greatest lower bound of B and A is A. Greatest lower bound of C and A is A. Greatest lower bound of D and A is A. Greatest lower bound of E and A is A. Greatest lower bound for F and A is A. Greatest lower bound for G and A is A. So this is all A. Similarly, we can calculate greatest lower bound of B and A is A. B and B is B. B and C is A. B and D is B. B and E is B. B and F is B. B and G is B. Similarly, we can calculate with C, D, E, F and G. We see that every pair of element has a greatest lower bound. So this is a lattice. Now one more example. Suppose this is the lattice. From this diagram also, here we have A, B, C, D, E, F and G. Here for the least upper bound, this is a table. Least upper bound of A and B is A and C is A and D is A and E is A and F is A and G is A. This is a least upper bound. Similarly with B, least upper bound of B with A is A, B with B is A, B with C is least upper bound of B and C is A, least upper bound of B and D is A. Similarly with C, least upper bound of C and A is A, C and B is A, C and D is A, C with C is C. C and E is C, C and F is C, and C and G is C. Similarly, we can calculate all other least upper bounds. For the greatest lower bound of A with A is A, greatest lower bound of B and A is B, greatest lower bound of A and C is C, greatest lower bound of A and D is A, greatest lower bound of D, greatest lower bound of A and E is E, greatest lower bound of A and F is F, greatest lower bound of A and G is G. Similarly, we can calculate greatest lower bounds for all the pair of elements. So each pair of element have a greatest lower bound, every pair of element have least upper bound. So this is a lattice. Now what is sublattice? A non-empty subset M of a lattice L together with a relation less than or equal to defined on it is said to be a sublattice if M is closed with respect to meet and join. Suppose xi belongs to M, it means x join y belongs to M and x meet y also belongs to M. Or we can say that if it satisfies all the properties of lattice. Suppose consider the lattice of all the integers under the operation of divisibility. This denotes divisibility. The lattice Dn of all divisors of n greater than 1 is a sublattice with respect to this operation. So we will find the sublattice of D30. D30 means divisor of 30 that contains at least 4 elements. So 1, 2, 3, 5, 6, 10, 15 and 30. These are divisors of 30. 1 30s are 30, 2 15s are 30, 3 10s are 30, 5 6s are 30, 6 5s are 30, 10 3s are 30, 15 2s are 30, 13 was a 30. So these are all divisors of 30. Now we need to find the sublattice which contain at least 4 elements. So sublattice, it will be a sublattice. Any element consisting of 4 elements will be a sublattice if it is closed with respect to join and meet. Means every pair of elements contains least upper bound as well as greatest lower bound. So one example is 1, 2, 6 and 30. We can easily check that least upper bound of 1 and 2, least upper bound means LCM is 2. This belongs to this. LCM of it can be easily checked that with respect to this operation divisibility, least upper bound of every pair of element as well as greatest lower bound of every pair of element belong to this set. It means it is a lattice. It means 1 2 6 30 is a lattice, 1 2 3 30 is a lattice, 1 5 15 30 is a lattice, 1 3 6 30 is a lattice, 1 5 10 30 is a lattice, 1 3 15 30 is a lattice. So these are all elements consisting of 4 elements which are sublattice of this D30. Suppose we consider the lattice L equal to 1, 2, 3, 4 and 5. So this is the given poset and this poset is a lattice. This is given to us because every pair of elements contains greatest lower bound as well as least upper bound. We can show this by making a closure table also. So now we have to find the sublattices with 3 or 4 elements. So any sublattice with 3 or 4 elements are those whose least upper bound and greatest lower bound for every pair of elements exists. So one of these is 1, 2, 5. We can check from this diagram. A set consisting of 1, 2, 5 contains greatest lower bound as well as least upper bound. This we can do by making a closure table. 1, 3, 5, 1, 4, 5, 1, 2, 3, 4, 1, 2, 1, 2, 3, 5, 1, 3, 4, 5, 1, 2, 4, 5, 1, 2, 3, 4, 5 is a are sublattices. These are sublattices consisting of 3 elements. These are sublattices consisting of 4 elements, and this is a sublattice consisting of 5 elements. Now distributive lattice. A lattice L is called distributive lattice if for any element A, B, C of L, it satisfies the properties A joint B meet C is equal to A joint B meet A joint C, and A meet B joint C is equal to A meet B joint A meet C. If these properties are satisfied, then the lattice L is called the distributive lattice. Suppose A, B, C belongs to lattice where L together with relation less than or equal to is a distributive lattice. Then A joint B is equal to A joint C, and A meet B equal to A meet C implies B is equal to C. To prove this, we know that B is equal to B joint B meet A. This is by absorption law. We know that B meet A is equal to A meet B. By commutativity, it means but A meet B is given to be A meet C. So A meet B is equal to A meet C. Now by distributive property, this is equal to B joint A meet B joint C. By this, it means B joint A is equal to A joint B, B joint C equal to C joint B by commutative property. So it means A joint B is given to be A joint C. So A joint B equal to A joint C, and this is C joint B, this is C joint B. A joint C is equal to C joint A by commutativity, and by distributive we can write C meet A joint B by this property. So this is equal to C joint A joint B is A joint C. This is given to us. So it means C joint C meet A joint C is equal to C meet C joint A by commutativity, and this is equal to C by absorption law. Now modular lattice. A lattice L is said to be modular lattice if for all ABC belonging to L, A less than or equal to C implies A joint B meet C equal to A joint B meet C. If this property is satisfied, then we say that lattice is a modular lattice. Now we have one theorem. Suppose L is equal to A1, A2, A3 up to A and B, some finite lattice. Then we will show that L is bounded. This will be a bounded lattice if it contains least and greatest element. Suppose L is equal to A1, A2, A and B, any finite lattice, and now we will show that it contains least element as well as greatest element. Suppose B1 is equal to A1, and therefore B2 is equal to A2 joint B1. B3 is equal to A3 joint B2. Bn is equal to An joint Bn minus 1. It means all B1, B2, Bn belongs to L, and Bn is less than Ai for all I 1, 2, 3 up to n. It means Bn is the least element of L, and Bn is equal to A1 meet A2 meet A3 meet An. because we are substituting the values here. Bn minus 1 from previous step, then b3 and so on. b3 is this, then b2 is this, then b1 is this. On substituting all the values, we get Bn is equal to A1 meet A2 meet A3 and meet An, and this is the least element. Similarly, we can show that A1 joint A2 joint A3 joint An is the greatest element. So this lattice contains least element as well as greatest element. It means it is a bounded lattice. Thank you.